Hey, hello everyone. Welcome to another session, another episode of the community stand-up, .NET and AI. We have a super cool topic to talk today. I see a couple of familiar faces here, like Jose and Luis and more. And hey, I appreciate, Jose, that the topic that I choose, I literally don't do a lot. I have these amazing people with amazing, super smart people with super cool topics. It's hard to see which is the next one because we need to see what we say yes and what we say no. But hey, I appreciate the feedback and hey, thanks everyone. Let us know where are you joining from. We are all here to help. And as usual, I will forget. My name is Bruno Capuano. I'm part of the Cloud Advocate teams. I do a lot of .NET. I try to do AI. I do my best. And I'm here today with Tal. Tal, hello.
Hi. So I'm a backend engineer. I'm going to talk about a bit production. So let's we'll get to that.
Yes. And hey, I am looking forward to the story of today because yes, it's kind of a clickbait about we are going to have blazing fast AI, inference, and more. Sorry about that. That's Copilot making kind of a clickbaity title. But hey, no, I appreciate Al. We've been trying to cook this for a month or two. Literally, the timing was kind of crazy here and there, but here we are. And hey, do you want me to share your screen and we can start, Al?
Sure. I thought you
So
had some things to share earlier, but
there it is. You saw your slides there. And as usual, I'm going to take a look at the comments. We have a 20 plus seconds delay between what the comments arrive and I see and more. But if someone has a question, we will try to answer that live. So all yours, Tal. Let's learn about this AI in a budget. Super fun.
great. So before we dive in, I just want to say that I'm not an ML ops guy and I'm not an ML engineer. So I definitely want to learn. So I had an entire journey in my previous company where they were doing a bunch of models in production. And so I had to learn a bunch of stuff. And we'll see the culmination of my understanding of the topic in a demo. So let's just jump right into a demo. We'll start with the Python code. So I took a random text classification model from Hugging Face, and I wrote the standard code of just loading it up and running it in batches. Nothing too fancy. So I'm just running chunks of 20 sentences. I found that that was the optimal number. And so we can see how well it does on roughly 70,000 sentences. So I'll just start this console app that will show the GPU utilization, and I'll get it running. So in the meantime, we can start talking about like what we're seeing here is a roughly 70-75% utilization of the GPU. That's the nice bar here. This is going to take a while, so get comfy. I'm kidding.
Hey, no, by the way, we usually, I think most of the time when we see these kind of things, we usually see the task manager with the Windows Tag Manager with the chart. This is a beautiful presentation. Kudos for you for doing this because I really like this console, whatever. I am going to ask the name of the app that you are running in the console to see this later. But hey, no, it makes sense. And I will assume that the big yellow lines are the CPU working, yes?
So
The
that's the
GPU, sorry.
GPU. The GPU working. The blue line is the memory consumed by the model.
Okay.
And this is a really small model. It's like half a gigabyte of memory. Oh, it just finished. And the app below is something I vibe coded with Copilot on VS Code. So, yay. So we can see that we ran a roughly 70,000 sentences in the model, and it took almost a minute. When I'm not streaming, it takes 50 seconds. And roughly 882 microseconds per item. And we got a really good accuracy, 98.86, which makes sense because I'm running the training set.
Okay, yes. We are
Now,
fitting the stuff where it's supposed to be, yes.
yes. So on the right-hand side, I'm going to now run the my solution, and then we'll dive in like to the background, etc. So let me just build the project, load the data, and we are done. Normally it's faster. It takes 3.5 seconds when I'm not streaming, but now it took 4.3 seconds to run roughly 70,000. It's 67,000 sentences. And so we're down to 64 microseconds per sentence instead of the original 882, which is more than a 10x improvement.
That's what I'm going to say. It's 10x plus faster, which is super cool.
Yes. So we'll dive into how we got there. But I do want to point out, I did do some quantization when I migrated to the .NET ecosystem. So like just out of the box from 32 bits to 16 bits, which is quite standard. So we lost a bit of accuracy, but we got a ton of performance. And if you actually retrain the model, which I didn't bother doing, but
yes,
if you have an ML researcher or you know what you're doing, then that's pretty easy and you can get the accuracy back. So let's just jump right back into the slides and talk about what did we just see. So taking a step back, you really can't ignore the elephant in the room, which is LLMs. They're an absolute great technology. They're general purpose. They're amazing at what they do. And everyone is now figuring out how to put them into their business application and automate some really complex, thank you, Pan. LLMs are really, really good. And they can automate really complex business-oriented applications, but they come at a price. Not only are they slow compared to what we just saw, but they're really expensive. Whether or not you decide to self-host or not, they cost a lot. So we're not going to talk about that for the rest of the talk. We're going to talk about something that was like really popular a couple of years ago. I know so much has changed.
Before we go there, I think Jose already shared it, but what's the name of the extension for the graphical interface? I think it's something for the NVH top, something that you use.
Yeah,
I remember I used HTOP in my Raspberry Pi back on the day because it's nice graphical when you're doing terminal and more. I didn't know that we have an NV HTOP, so probably this one. And then we have another question here, interesting, which is, do you have 12 gigabytes of memory dedicated or shared for the GPU part?
So I'm running on my local machine, which I'm streaming from. So I have an RTX 360, 12 gigabytes version. So just home grade hardware. I'm not running on server grade hardware.
Home gaming standard hardware, nothing.
Yeah, not even the high end. Like I'm on the mid tier.
Yes,
so
I am saving other question like this one for quantization and more for the end. So Nature Yogurt, we are going to see you there. But yes, I want to know more. And hey, thanks for not talking about LLMs. It's all about LLMs these days. So let's do something else.
Yeah. So if we go back a couple years, it's just a couple years, by the way, when the business needed to solve a complex problem, they would isolate a dedicated portion of it that's really hard to hard code logic using code, and they would train a dedicated model.
Yes.
They're specific to a specific task. They have a specific input, a specific output. For example, text classification or like understanding what entities are in sentences or videos and tracking them, etc. There's tons and tons of models out there. Hugging Face has literally thousands, which you can just pick and choose the best one to start from. And the promise with dedicated small models, I'm going to call them small because they're small compared to LLMs. They used to be big, but now they're considered small. The main benefits that they promised was that they're going to be fast and cheap. But a lot of deployments get that wrong. They should be fast and cheap, but they aren't. And the reason is the tech stack. So let's dive a bit into that. So the standard tech stack for these models, as I said, we're going on Hugging Face models because that's pretty much where everything goes. And it's up to these three pillars. We're running on Python, we're using a PyTorch model, and we're wrapping everything up in a Hugging Face transformers pipeline. That's the standard tech stack. That's what most of the dedicated small models used to run in, or still do, but it's less popular with the LLMs now. But this tech stack comes with a bunch of things that hinder production. We're talking about production inference. We want to reduce costs in production, and we want to serve lots and lots of clients in the same time. And Python has a very big flaw or design decision that prevents us from doing that. And that is both the GIL and it being an interpreted language. So for those who don't know what the GIL is, each access or each time you want to run a chunk of Python code, you pretty much have to take a lock, and it's a global lock, and you can't really do multi-threading. You can do multi-processing, but that has overheads. And when we're talking about GPU utilization, it's pretty much a no-go. And when you're doing interpreted, you have pretty much eliminated like 99% of the optimizations that you can do in a compiled language. I can't do inlining. I can't do deciding how my variables are going to be structured, because everything's a dictionary behind the scenes. So you keep on having branch mispredictions, etc., and that just hinders your performance. So those two design decisions really hinder production. Then we're going to go up the tech stack a bit. And PyTorch and Hugging Face, again, are great frameworks, really great. By default, when you load a PyTorch model, it's unoptimized. And when you pair that with Hugging Face being framework dependent, we'll talk about that specifically a bit later, but the actual implementation of Hugging Face is framework dependent. So if I want to use a specific tasks, I'm stuck with PyTorch. So that combination prevents me from actually being optimized. And I tried to optimize PyTorch within PyTorch, and that's like, you have to be a genius. I haven't figured it out yet. I've been trying to for the last 2 years. Please send me links to learn. I really want to. And the main reason I point out for these two things being the case is because the purpose is not production. It's training models and getting to the cutting edge research and development of the next model, which is going to outperform accuracy and be able to generalize better, etc. And so they're great at that. But I'm talking about production. And in production, I don't need training. That is, I already have a model, and I'm not doing R&D. It's already been done. So I want something that's optimized the best, and PyTorch and Hugging Face sadly do not do it. And last thing, all of this is wrapped up in a very big Docker image. It's really common to see 6, 10, 12 gigabytes of a Docker image that I need to now deploy to production. Just pulling the image from the container registry can take 3.5 minutes, including the unzipping, etc. So startup time is really bad. So putting that all together, you get that this entire tech stack is really hard to optimize, and it's really hard to get a good production deployment. So can we do better? Don't know. Let's look at the current design of the Hugging Face pipeline. So I said before that it was framework dependent, and it is in a sense, because this is a standard pipeline in Hugging Face. So you have a text classification pipeline, and this is an example of a text classification pipeline. So I have a pipeline for a specific task, which makes sense. Each task would have a different pipeline, a different pre-processing expectations, and different inputs and outputs of the model, and different post-processing. And thing is, though, that the entire internals of each pipeline is tailor-made to the specific framework of model that you're running. So in our case, we have a PyTorch model, and the interface expects it to be a PyTorch model, and the output and the post-processing all works with PyTorch tensors, and it's really, really difficult to now implement something for a different framework or getting your optimizations somehow in there. So really hard. So now we can take a step back and say, what are the design goals of the optimal production grade framework? Well, I would like to have high utilization of my very expensive hardware because it's expensive. So I want to use it to the maximum ability of it. I don't want to leave even 1% of performance on the table. I want it to be low latency and high throughput, because if I can serve you faster, that's better. And if I can serve multiple people at once, that's even better. Now, normally there's a trade-off in between the two, but because of how GPUs and tensor processing units work behind the scenes, that's not always a trade-off. But we definitely want to be able to make that trade-off when it matters. We would like to be able to toggle lower latency and maybe have less throughput, or maybe the opposite. We would like higher latency, but we can serve more people at once. All of that we want with cheap abstractions, faster startups, all while utilizing smaller images. And so I was dealing with this in my at the startup that I was working at, and I'm a .NET fan, and I see that there's a new launch of a .NET version, and I go and I see what's going on there. And so why .NET for ML workloads? Well, if we just look at .NET, we get a really highly optimized language, which is C#. It's a great language, really easy to set up, really easy to work with. And then we place on top of that a highly optimized web framework called ASP.NET. And we have a wonderful ecosystem on NuGet with out-of-the-box performance for any workload, great frameworks all around, libraries that are optimized, curated. A lot of people say that like .NET doesn't have as many libraries as the Python or the Node ecosystem, but each one of them is optimized and tailored and really, really well at what it's doing. But that's just .NET. What happened in .NET 9 that changed the scene for ML? Well, we got AI abstractions, and we got tokenizers, and we got tensors, which is exactly the missing pieces for an AI deployment.
Yes, and hey, fun fact about that. I really can't remember. I am the worst. I've been doing this, and I am the person who's supposed to know this. But a couple of episodes ago, I can search if someone is interested. We have someone from the .NET team, Tanner, and they basically explain how is the current implementation of tensors, the tensor span, how they're going to be even better in .NET 10 and more. Yes, .NET 9 was the big jump for anything ML related, not even AI, ML related, because we have these kind of things and they really work right now. Before we are dealing with, and I tried to do this in the past also, with crappy arrays and crappy float arrays and more. This is really, really great. And hey, I need to connect this session with the previous one because this is amazing. Tanner is going to be super happy about this. Sorry, Tal.
Yeah. I'll just say that when I was working on this, I actually opened up a ticket to the .NET team, and I talked to Tanner and I talked to people on the semantic kernel team, and we got a bunch of APIs. There's the weekly session of the API review, and I've actually had a bunch of conversations there with the team. So great interactions with the community, great feedback loops. And so a lot of stuff that I'm going to be showing today, I'm going to be doing on .NET 10, the preview. And I'm actually using preview packages that already include a lot of the feedback, not from just my feedback, but other people in the community that requested tensor and tokenizer related improvements over what was already shipped a year ago. So these were the exact missing pieces that I needed in order to get the ball rolling. And I created Phi.net. The name is still like iffy. I'm not sure about it, but for now I'm calling it Phi.net, which is short for Fast AI on .NET. And the basic design is very similar to the Hugging Face pipeline, but I think I have improved on it exactly where it's important for performance. And of course, it's on .NET, which is great. So these are the major components of the library. Of course, you can do your own design and use the building blocks, but this is my design. You start with the algorithm. I'm trying to solve a business problem. For that, I might need to orchestrate multiple models working on different subsets of the user input. And so I would like a pipeline that wraps the entire run of the model. So that's really easy to write my algorithm, not caring about ML. The pipeline could have been behind the scenes like a regex working. I don't really care. But just like get an input, get an output, and that's like human readable inputs and outputs, which is exactly what the pipeline does in Hugging Face. But here's a bit of the twist. Behind the scenes, I'm going to be using batch executors because we know that batching is really important, and it's really important to utilize every single ounce of performance. So I'm going to plug in something that allows you to optimize your model for your use case, whether you're doing offline batch processing into a database or you're doing online web applications and you need to stream everything so that you're highly optimized with async await. Great. You choose which batch executors you use for your use case. Now, we want an inference step. Like, these are the steps that we actually need to do to run the model. This is the pre-processing. This is the actual run. This is a post-process. And that is like task specific. So that is the text classification, right? We want to have a text classification. We want to have a video object detection, etc. So we want to write that once and use with whatever framework of model. So for that, we abstract the model executor. We don't really care. And so in order to do that last step, the model executor, I need to have an interchange type. I need to be able to pass in tensors and get back tensors, right? So that's exactly where the tensor, the built-in tensor in .NET comes into play. I have a single interchange type that all of the different executors can comply with, instead of the other way around where I have to re-implement my inference steps for each different framework. And of course, we have hardware. So the core concept behind the library is that everything is plug-in, everything is interchangeable. And so you get to choose the hardware that's right for you. You get to choose the right framework. On top of that, you can implement your abstraction once, your ML task once, and reuse anywhere with any model on any framework. You can split your work optimally for your scenario, which is critical. And of course, we want a friendly API. And of course, we want to have the algorithm working and maybe do some really cool plugins with ASP.NET or an offline batch executor, etc. So we'll now dive into like a demo, and we'll see like how my library achieves the performance we saw beforehand. Let me just kill the different apps here behind the scenes so that it doesn't destroy my GPU, and jump into code. Cool. So I'm going to run this, and we're going to go through the code while we run it. And we'll start with the fact that I have a model directory and I have an evaluation manager. Nothing really fancy going behind the scenes with the evaluation manager. It's just loading once the training data and running multiple times with different inference configurations. I'm slicing it so that we don't have to wait the entire time for the entire batch. And nothing fancy going on here. I'm just calling batch inference and measuring the time. Of course, ask questions.
We'll probably join later, but yes, Ellie, if you have a question, Ellie Fast, sorry, if you have a question, drop the question. I am following the comments. Try to answer in the comments or live. It's if it's longer. But yes, let's go there. And by the way, kudos to our friends from JetBrains, because we haven't seen riders in a while, and I love it that we have rider. We talked about this before starting.
Yeah, it's really fun. I like working in VS Code or Rider, depending on what I'm doing. Really great products. So I'm using ONNX, which is a different framework for running models. It's highly optimized. I'm sure there are great sessions on it. And the configuration is really, really fun because I can change the hardware that it's optimized to. For example, I'm registering here my CUDA, but I could have easily run this on a Mac and registered the relevant libraries or use AMD's specific library, etc. So really, really cool that you can just switch the hardware and it just works. I'm loading my tokenizer, I'm loading my model, I'm building my classification task with the different classification results, that is false and true. I'm using the tokenizer, I'm using the model, and I get a text classification task back. And now I'm wrapping it in my serial pipeline batch executor, which does the exact same thing that the Python code did. It chunks up to a batch size and runs each batch sequentially, so serially. I'm wrapping it up in my pipeline, which gives me a really nice interface, and I am plugging it into my sentiment inference algorithm. So if I just like show you a predict example, we'll look at the code in a second, but I'm just running this cat is very cute cat, which is of course positive. Like that's a positive sentiment, right? So I expect it to return true. So I do. The sentence, the cat is very cute, and it's true, which is great. It works. And if I want to run a batch of sentences, I can just pass that into the batch predict, and I loop over the results. And as customary, when you run batches, the first index of the input is the first index of the output, and you just match it up. So if I just run that, it's done, and we get all the right sentiments. The weather today is terrible. It was really, really hot today, and so bad sentiment. So again, this is just like normal. You would expect this from a library. You can run predictions. Let's actually look at what's going on behind the scenes, because otherwise, not really interesting. So if we look at the text classification, we actually have the tokenizer and the model executor. As you can see, this is an abstraction. And this, by the way, wraps the tokenizer abstraction. So we'll see that in a second. But I'm also using the tokenizer abstraction that was introduced in .NET 9. And if I look at what's going on, I am doing a pre-processing step where I am tokenizing a batch, and I'm passing in the input, and I return a batch result. Because I also have I have two tensors here. Again, the interchange type is really important here. I have two tensors, and I wrap it up into a result. Let's look at the tokenization. I am going to be calling the tokenize, and in the innards of the pre-trained tokenizer, I'm calling the function which is encode to IDs. I'm doing something here illegal, don't do it, but behind the scene, this returns an iRead-only list. Everyone knows that behind the scenes it's a list, so I can access it with high performance. I'm casting it. Sorry, don't do this, but I'm gonna do it. So back to this loop. So I've tokenized each sentence separately, but I actually need to pack it up into a tensor. So I've pre-allocated here a span of the lists. A span is just a wrapper, and I am doing I'm actually using the new abstractions from .NET 10. These are the .NET 10, where I can do a dimensional tensor, where pretty much they give you like an enumerator over the specific dimension. So if I have a batch and I want to access the tensor in batch location 0, 1, 2, this allows me to do that really efficiently. And so I put the tokenization into the row. Here I'm using a bunch of span stuff, and I'm using tensor primitive abstractions, and I'm building on the fact that .NET automatically has safety. So when I created the tensor, it's zeroed out, so I don't have to fill it up with 0. No need, it's already pre-initialized to 0. And if the padding token is not 0, only then do I need to fill out the fact that fill out the padding token. But if the padding token is 0, it's already done. I don't need to do it again. So that saves a few milliseconds, but each millisecond counts. Microseconds, sorry. So that's pretty much the tokenization. And as we saw, we are using all the new great stuff in .NET 9 and 10. And here we're actually looking at calling the model. So we have a model, we execute it. And before we actually dive into what's going on behind the scenes, for performance, I have put in here a callback where I get a tensor span back that wraps the native memory that's already like in the ONNX execution. I get it back here. I don't need to copy it twice in order to use it. I have a callback that gives me it, and I just run on dimensions and get a classification result, which is of course using a bunch of math which I copied over from Hugging Face. This is how you do it. So I'm using a softmax, and I'm using index and max, etc. So all of that is great. And I'm using all of these really cool stuff that came in. Now, if we go back to ONNX, I want to call a model. Again, the model is I'm using is on ONNX, so they have their own ORT value type thingy, but I get to convert it from my read-only tensor span to this because it's an interchange type. So the ONNX team has added in a conversion. And I have on the result of the model, I get, again, a conversion back from the ORT specific value to the interchange type. So I get it back here. Again, without these things, it's really hard to do a generic library because then I would have to have a specific ORT value callback, which only works with ONNX, and I'd have to re-implement everything. So really good.
I'm sorry to interrupt, but I think a very important point to share right now, it's basically Zach is asking, hey, we are going to forget about Python in the future and switch to C#. Python has an amazing community. I mean, we trash talk with them because we love Anthony, Pamela, Marlene, everyone there. And these are my colleagues, by the way, from the Python team. It's amazing Python. And yes, we can do a lot of things on C#. But what Tal is talking right now is literally something that not even people see in Python. In Python, people do Hugging Face, import, create a pipeline, text classification pipeline. They did the model and they go for it. So this is kind of the deep foundational whatever is happening in the back that nobody cares in Python. And yes, we have, as you literally said it, we have amazing libraries in .NET to do stuff. .NET 10 is ready to rock with these new tensors and more types. And I love that you also mentioned that I didn't know that you already talked with Tanner and the team. I try to remember everyone that .NET is open source. You can ask questions, you can suggest improvements. We want to do a lot. But I am going to literally say this again. A lot of people in Python are using libraries from Hugging Face, an example, but I would probably say that not a lot of people go deep to understand what is happening. They just use it.
Exactly. That's exactly the point. The point of Hugging Face and PyTorch is to, in each appropriate step to the understanding that you need to get to. Hugging Face, you import a model and you run it. In PyTorch, you don't need to care about the tensors too much. Like you use you like call functions, and there's a bunch of wrappers. You call an attention block, etc. And the tensors is happening behind the scenes. Here we've actually gone into the crux of like, what does Hugging Face do with the tensors that it gets back with the model? So I had to recreate that in C#, and it was only really available to do in a high performance compatible plugin way only a year ago. And I do think that Python is great, and Python with PyTorch and Hugging Face is going to stay for years, probably forever. But for production, I do think that the MLOps story of like you train your model in Python, you have your ML researcher, fast iterations in PyTorch and Hugging Face, and you get your model ready. And then you have a publishing step where you publish an artifact to a C# deployment. And I think that can work really, really well. There's, of course, lots of details to work out there, but I think it's doable.
And yes, and the key piece here, it's literally everybody's going to pay for this GPU time. So when you start to think about money, which is optimization, but at the end, the nice thing about the cloud or whatever is that you pay for what you get. And hey, if you have option A and option B is faster and literally use less resources, you're probably going to go for option B. Once again, not trust tag into a Python friends, but hey, when we have these kind of scenarios up and running, it translates on, okay, this is cheaper and faster. Everybody will say yes for this. Sorry, Tal, it was a small parenthesis that I want to tell to everyone, because
really
this is not
important one.
Yes, but people in Python don't see this. Not a lot of people go deep to understand what is happening there. And I like that because it literally opened the door to a lot of people using models in their machines and do stuff. Now we have a very, very similar approach in .NET, which I love. So, hey, back to you.
Great. And last thing I wanted to show about the actual algorithm from behind the scenes is that when you come to work on, like, you want to do sentiments inference, well, what do I have to do? Well, all I have to do is implement my algorithm. I'll get my model from the ML researcher, but I just have to import the pipeline. I say what's the input and what's the output. So I get a tokenizable text as input and a classification result as an output. And this model, this inference algorithm is really, really simple. I just call the pipeline to get a result and return it. But you can imagine when you actually, where small models shine is that you can run multiple models on the same machine and have them chain results to each other. So for example, you can run one model that does embedding and retrieval from a vector store, and then rank the results that come back with a different model, and then return the best optimized search result to the user. That's a pipeline, right? So you call two models, you run one pipeline, you run the other one. You can run them in parallel, and you can have one request on the first stage and another request on the second stage, and they're both using the GPU. And you can highly optimize these types of scenarios. And so you write your algorithm, and just like Hugging Face, you call a pipeline, it works. You really don't care what's going on behind the scenes. Same thing with batch tokenization. Nothing too fancy going on here. I did a bunch of fancy stuff because I know a bit about optimizing, like with spans and stuff like that, but not really super, and nothing super clever happening here. I'm even using link because it's not that slow for this specific scenario. So let me close that, and we're going to go back to the program, and we're actually going to run a bunch of batch predictions. Now, I'm going to show you how much time it takes to run just 10,000 sentences in the Python, just so we can have a baseline of like what. I don't want to run the entire data set again, but like if we just run the first 10,000 items again, so that'll be up here. We should see that it takes about 8 to 9 seconds. So let me see.
Yes, it's probably going to take a little longer because your GPU now is streaming and you have your camera and more. But hey, there it is. 8 to 9. Yeah. Perfect. You nailed it.
Yeah, I made it. 8.8. Great. So we have to be 8.8 seconds, right? So let's see this different components from my library that I'm placing together in order to optimize this specific model on this specific scenario. Again, because we're talking about super high utilization, you're going to have to do this. You're going to have to play with your model, and you're going to have to run it multiple times with multiple batch executors and different parameters. But you want to get it right. So we're going to do 10,000 samples, and let me just close this up. And we'll go with running the same thing again. We're running sequentially 20 sentences in each batch. We're using ONNX instead of PyTorch. Let's see what the baseline for just running sequentially is. The same algorithm, right? 20 yes. In a loop, 20. 2.6 seconds. So already we're a lot better. Now, out of this, 2x is from just turning from 32 bits to 16. So we have to wipe that away. But the other is from migrating from PyTorch, which is a training first, R&D first framework, to ONNX, which is production first. Great. Well, that's just stepping in. We just moved from Python to C# and to my library and ONNX. And well, what can we do to actually do better? We don't want to just do the same algorithm. We want to optimize. So now we get to the stuff that you get out of the box in C#, which is channels. I can have in-memory queues that pass with different threads, reading from the queue, writing to a different queue, and I can have this entire stream running with different threads. So I get an input on one thread, I read it from a queue, I tokenize it, I send it to a different queue, I run the inference, etc. So I've split up my model into multiple steps, and I'm running each step on a different thread reading from a queue, which is really, really cool. And doing that in Python is not efficient because we have the GIL.
Yes.
So now behind the scenes, it's not really, really complex. I'm using channels, which is a library that comes out of the box in .NET. It's super optimized. It's used all over the place. It's really, really good for in-memory queuing. And I'm just running two background workers, one for reading the model and one for reading the output from the model. And it's not doing anything crazy. When I get a batch, pretty much, I'm not going to go into the continuation. It just looks like this. You run a pre-process and you get a writer to the channel and you write. What am I writing? I'm writing a streamed inference chunk. I'm like collecting all the results on the chunk and passing it in as we go. So that's really, really cool. I have an option to run the pre-processing in parallel because I'm getting a batch each time, so I can run that in parallel or not. And let's compare what's going on. So again, I'm not running the tokenization in parallel. I'm running 4 different threads for each stage. So the model is using 4 threads behind the scenes, which is really cool because I'm reading from a channel. I can parallelize that as well. And of course, I'm chunking it up and I'm using the classification task. I'm wrapping it up in my pipeline, and etc. So now I'm running it, and we're going to see an improvement. It's not a major improvement, but of course, when you multiply this by the millions of sentences that you're trying to process daily, this small reduction can translate to a lot of money. And you say, well, you didn't parallelize the tokenization. Well, how much would that have saved us? So let's run that as well. And we got 2.3. So this is actually something I was hoping for because the numbers sometimes switch here, like one is faster than the other. So yes, within margin of error, it's the same. Not always throwing more threads at something will always help. Depends how taxing the tokenization, what's the average length of the sentences that you're tokenizing. I mean, there's a bunch of stuff that goes into how each scenario you need to optimize, which is why it's a toggle. You get to choose. Now, these optimizations are runtime scheduling and not specific for text classification. So let's talk a bit about how does text run on inference on GPUs. So if I have sentences, as we saw, I have it open here. I've got the data from the training set. Each sentence can be really small, really large, and they're not the same size even comparably. You can have a sentence of 2 words and one of an entire paragraph. But a GPU works on an image. It was designed to produce frames from games. So it wants an array. It wants an array of 2-dimensional, 3-dimensional arrays where it's fixed size and all the values are full. So we have to introduce padding. Let's say there's a batch break here that we've scheduled that this batch is one batch and this is another. So we have to fill it up to the largest sentence in the batch. So for here in this example, I had 10 padding tokens, which is normally 0, to the first batch, and I had to add another 4. So 14 padding tokens I've added to this specific example. Now, the padding tokens are compute that goes to waste. The GPU has to run the same calculations on these padding tokens as if they were real tokens and just ignore the results in the end. Yes. Which is a shame. We're just wasting cores on the GPU. Can we, and I know it's like it's hinted here, can we
spoiler.
can we reorganize the work so that there's less padding tokens? And the answer is yes, you can sort by the number of tokens. And so in this example, if you sort it, you get that the first batch, which is standard, let's just say like the first three sentences and then the next two, right? So we got 4 padding tokens, 2 padding tokens, and another 2. So we went down from 14 to, let me do math, live 8. So almost twice as much less padding tokens. That is a lot less compute that's going to the trash. And if I'm running these 2 batches in parallel on different sectors in the GPU, I get to utilize more cores because it's wasting less cores on padding tokens. So how do you do that? In my library, you just use the stream batch, because we definitely want to parallelize the different sections of the processing, but let's just sort the input. I'm not doing anything fancy here as well, because I'm just like, I am parallelizing the tokenization in this case, but I'm just sorting by token count. This is a special comparator that I wrote, which just looks at the tokenization and it caches it, etc. And as we said it previously, the first input must match the first output, so we have to unsort it. We have to get back to the original order. So in the middle, I'm running a different batch executor, the internal one. So I get to use this as a plug and play, as a decorator for something else. So if I go back, I'm wrapping, I'm passing in the stream batch executor as an input. I've decided that that's the best for this specific model on my specific hardware. And so I get to wrap the different executions. Of course, I'm doing pipeline, sentiment, inference, and I'm running the evaluation. So last we run was 2.3 or 2.2. And if I run this again, I'm down to 0.9. So we finally gotten underneath 1 second. And so this actually shows the difference in between like general optimizations. Like I'm doing better scheduling, I'm doing better thread management, etc., and optimizing to the specific task at hand, right? I've understood the hardware I'm using, I understood the algorithm, I understood the inputs, and I've optimized to that specific scenario. And of course, this is plug and play. So if your specific scenario has totally different inputs, and you know exactly what's going on, you can optimize the scheduling and the splitting and everything to your specific scenario. So this is already under a second for 10,000 sentences, right? Well, can I do better?
No, we still have one more.
Yeah, so we can do better. And so if we go back to this example, well, let's say I have the 10,000 sentences. Well, maybe I'm not utilizing the entire context window, right? Like each model has a context window that was like designed for. Well, maybe I did not reach that. Well, if I just statically cut into chunks of 20 sentences, I might be losing performance because the 20 sentences might have all been tiny sentences. It might have all been 2 words or 1 word. In the training set, by the way, there's at least 1,000 sentences that are 1 word each. So we're going to dynamically change the batch size according to the token count and the padding ratio between the actual tokens and the padding tokens. And we're going to slice into different sizes. Now, this works really well for offline.
That's so
batching.
cool. Sorry.
Yeah,
This is me getting excited about this. So sorry about that.
So instead of slicing like fixed size, we're actually going to be dynamically. Now, in order to support this scenario, I still want to use the stream batch executor, but now it's not doing the slicing. It just gets a batch and runs it, right? But I still want to reuse the fact that it's running the different threads and different workers and its background processing, etc. But definitely. And so this is now dynamic, and I've run like dozens of parameters here in order to get to these numbers. 2K and 0.1 was like the best option that I've found. I'm still using the token counting because it's only looking like it's collecting sentences. The implementation here behind the scenes is collecting the sentences until either this is breached or this is breached. And then it sends it to the GPU. And so by sorting, I get to run this a lot faster. And so we're down to 0.93. I hope the streaming won't ruin this. We're down to 0.7.
Okay, that's cool. Even better.
That's really cool. When I ran this offline, I got 0.66 pretty consistently. So if I remind where we started at 883 microseconds per item. We're down to 66, sorry, 71 or 66 microseconds per item. More than 10 times improvement. Just translating that a bit to like the MLOps story, that's 10 times less machines.
Yes.
Also, something that's not reflected here, because this is like batch processing offline, etc. When you run this type of scenario using a web framework, and you compare the latencies of Fast API, for example, which is the common API used to serve models on Python, and you compare it with ASP.NET, you're also talking about a latency decrease from roughly like 100 milliseconds to like 9. So even the latency is improved considerably. I still don't have a working demo with benchmarking for the ASP.NET story and comparing that with Fast API, but I'm going to do that someday. I need time. So I think that's enough for the demo. And back to the slides. So what's next for the framework, the library? Well, I want to implement more ML tasks. Right now, there's 2 implemented, which is text classification and multiple choice, where you give it the model multiple options and it chooses the best one for the context that you give. So like you give a question and then you give the 4 possible answers, and then it chooses the correct answer. So something like that. I want more input types. So right now there's only text. I want also video, images, mixed, etc. And I want more ML frameworks. I know that I kind of said that PyTorch is not ready for production, but so many models are already on PyTorch, and exporting them is difficult and not always supported. And if you want to run multiple model that doesn't fit on a single GPU, ONNX doesn't have currently out of the box something that works. So you have to stay on PyTorch or a different framework. So I want to have some integration there. I want better integration with the .NET ecosystem. I want some type of evaluation pipeline, whether it's like you just want to run a few models, compare the results, the accuracy, etc., or you actually are doing like batch processing, offloading to a database. And the most important thing is this project is not yet ready for production. There are no tests, no coding standards, no packaging, no pipeline for like deployment, etc. So I want to get that all sorted. I'm still learning. I'm still new to that, but I think that it's not that far away, especially with AI helping. And with that,
question here that I realized that I created the episode, the resources and more, but I didn't add the repo.
So it's under my username, tjwald /5.
Yes, I am going to talk with Tal. I'm going to add it. We have a resource with all of the .NET 10 downloads and more. So we are going to add it there so people can take a look, as you mentioned. And again, as you said, it's not ready for production, but it's an amazing, amazing example of what you can do to optimize this process. I love it.
Yeah. So to summarize, when you're using the correct tech stack and design, which is C#, .NET, and Phi, you can build cheap AI solutions that are fast and accurate and have scalable solutions, whether it's APIs, as I wrote in the slides, or background jobs just running in the background. You really want to optimize that to be the smallest amount of machines possible. And with that, I think we have time for a few questions, if anyone wants.
Yes, I mean, we don't have a lot of questions. We already answered most of them online. The only one that we have here is Natur Yogurt asking this question, that if we can basically fit this into the grid block, into the GPU level.
Yeah, so my library does not actually deal with the model. I get the model, you get to do whatever you want within the model, and then my library runs it. You can do threading, batching, grids, block level, all that when you're dealing with the model, like the internals of the model, my library does not deal with it. So if you get a more optimized model, then this will run faster. If you have a less optimized model, then this will run slower, but it will optimize the entire scheduling around it so that you get the best performance for that specific model. I have another example in the repo of the multiple choice. That's a BERT model. That's the larger one. And so like the Python example takes 7 minutes and mine takes a minute, even though it's a larger, slower model. So definitely, I still want to learn CUDA and stuff like that, but I don't know. I don't know how to do that. And that's within the model.
Yes, and hey, we have people saying, we have here Marisa saying, well done, awesome project. Jose is also asking if you have your GitHub is tal.
That's actually my employer's my previous employer's GitHub. My current GitHub is TJ Walt.
Yes, I don't worry about the resources. If you're watching this, it's going to be updated anytime soon in the resources. And hey, people want to run the library and more. Hey, this was great, and also it was a perfect timing. I mean, literally on time. We usually you're the best guest ever here. Make my life easy and more. And hey, once again, not sharing, not trash talking or talking about Python is amazing, but yes, there is a moment, as you mentioned, that when you move to production, these things are important because you pay the GPU cycles, you pay your stuff. So everything that we can save here and there is amazing. And this is a great example. I love also how you frame this whole story as a learning process and what we can do using the latest and greatest about the .NET 9, .NET 10, Tensor Span, and more. Hey, I love it. I love it.
I would like to shout out again to the team. The .NET team is doing an amazing job, not only in performance, but choosing the right APIs to enable every scenario possible and the best performance possible is really difficult. You can see different ecosystems getting this wrong again and again. And they're doing the best they can, and they're doing a good job. And those libraries they're producing, the APIs that they're producing, the framework that they're producing, absolutely wonderful.
Yes, and if someone wants to go deep there, take a look at Stephen Toth every time that he's talking about improvements on the .NET libraries and more. And he always have, I can't remember the exact sentence, but he always said there is always a space to do better. It's amazing how we are in .NET 10 and we're still improving stuff, but hey, very smart people, amazing people, by the way, lovely people, and they always do better. I like it. Tal, thank you very much. Thanks everyone in the audience. I hope everybody have an amazing rest of the week. I hope it's not super wet and hot there. Hey, we have our fair. This is Canada. It's not supposed to be also so hot, but we are dying also here. So hey, goodbye everyone. Have a great day.
Thank you very much.